about the orthogonal Shimura varieties because Eugenia already explained it very well. So we have this kind of, which I call orthogonal half plane, and then let's say we have a lattice L, which is of signature n, 2, and then maybe a finite index subgroup of OL, and then this of course acts on Hn, because it's very clear here from this description, and then this quotient Hn mod gamma would be then in this case called the orthogonal Shimura variety, and this is non-compact, as Eugenia explained, and it can be compactified by adding finitely many cusps which are either 0 or one-dimensional. And then this is called the Baily-Borel compactification, which is the object that I want to discuss here. In particular, I want to somehow look at what is the Picard group of this compactification, of this Baily-Borel compactification of this orthogonal Shimura variety. And the way we're going to attack this problem is we're going to somehow use the connection between the orthogonal side and the symplectic side. So we all know from theta correspondences that there is somehow an information exchange, and we're going to use a result on the symplectic side to say something about the orthogonal side. For this talk, I will make a few assumptions to make things easier. So I will always assume that L splits of two hyperbolic planes, and so there remains something which is positive definite. And I will also assume that gamma is equal to this discriminant kernel. So L prime is the dual lattice of L, and this quotient L prime over L is called the discriminant form. It's a finite abelian group together with a non-degenerate quadratic form, and I call this discriminant form or finite quadratic module if you want. And then, okay, gamma is this kernel, is the elements that act trivially in this thing. So now let me make a small excursion to the symplectic side. So I will talk about the Weyl representation. And so now this positive definite lattice M will play an important role. So M is positive definite, even lattice, and here I assume of even rank, although this is not important, this is just for this talk to make things easier. And M is the dual lattice. And then we can define a vector valued theta series, which lives on H, which is the usual upper half plane, and takes values in this complex vector space where you have for each element, each coset here you have one dimension, so to say. So this is the group ring of this, or group algebra. And it looks like this. So you have component function, and each component function you sum over the corresponding coset, and then this looks like it usually looks in a theta series. And if you plug in an element in SL2 set here, gamma tau, then this looks already a lot like a modular form. Just here you have a representation on this space. And so in fact this is exactly a modular form for the Weyl representation, which is this, a certain representation on this space. Now we can make things a little bit more interesting by adding polynomials here as weights. So we have a harmonic polynomial of homogeneous degree. We add it here as a weight, and then this increases the level, the weight by exactly the degree of this polynomial. Yeah. So then it's still a modular form of weight m half plus nu in this case. Okay, and now maybe I call the space of cusp forms for the Weyl representation of weight k sk of d. So d is now just a general discriminant form, any discriminant form, and then this maybe I call it a space of cusp forms. And then I also want to define the space of theta series. So what this is, it's essentially the span over all theta series in a given genus. So these would be the lattices that are positive definite of rank m, and that have m prime over m is this discriminant form, and they form exactly one genus. And here I take the span over all of these, and I also allow all polynomials of the correct degree, so that the weight is in the end k. And okay, these isomorphisms between these discriminant forms is just to get them into the same space, space, so to say. And then there's essentially, this is the main result of my PhD thesis. It's called the basis problem. So I have showed that if the rank of my lattice is greater than 6 and locally you split off a hyperbolic plane, so this means over set P, this splits off a hyperbolic plane, then these theta series span the cusp forms. I have only showed this in the case when the rank is even. And then together with my collaborators, we also did the odd rank case, which is the same proof, but it's more technical because What makes it a bit annoying, the odd rank case, is that you need to work with MP2 set instead of SL2 set, and that's a bit more technical. Okay, so let's now get back to the orthogonal side. So I also define this space of almost cusp forms just to make it a bit more easy. This just means we have the cusp forms, and there's also one Eisenstein series. In general, there are more than just one Eisenstein series in this vector valued setting, but here these almost cusp forms, I mean just a space consisting of cusp forms and only one more Eisenstein series. And then there's this nice result by Bergeron, Lee, Milson, and Möglin, and Lee is my collaborator in this case. And that says that if n is greater or equal than 3 and we split off two hyperbolic planes, then the Picard group of this Shimura variety, but this is just the inner part, not the compactification, complexified, this is isomorphic to the dual of these almost cusp forms of a certain weight. And okay, and then there's another result by Jan and Freitag, which says that the space of obstructions for extending a line bundle here to the Baily-Borel compactification, this space is given by these theta series. So we have here rank n half minus 1, and then the weight is the same as here. And now we can use this result on the basis problem, which says that this space is the whole space of cusp forms, which means that every cusp forms poses a obstruction for extending L. This means the only line bundle which can be extended must be trivially here as a linear form on the space of cusp forms. And so since this is just one Eisenstein series remaining, this must have rank 1. And this then brings me to the main result, which says that if we have even lattice of signature n, 2, n is greater than 8, and we assume that L splits two hyperbolic planes, and we assume further that it locally, so for every p, splits 3 hyperbolic planes, then the Picard group of the Baily-Borel compactification of this variety is Z. From what I have explained to you, we only have showed that it's Z plus some potential torsion, but then you can somehow show that this is torsion-free, which is a purely geometric argument, so there are no modular forms involved. And why is this interesting? I mean, okay, maybe you find it interesting on its own, but in particular, there are many moduli problems where these orthogonal Shimura varieties appear. So for example, if you have the moduli space of quasi-polarized K3 surfaces of genus G, this is a orthogonal Shimura variety like this that satisfies these conditions, and so we have showed that the Picard group of its Baily-Borel compactification is Z. And there are also some other modular problems that are really the Baily-Borel compactification has a modular interpretation, so it's not just the compactification of the moduli space, it's really the moduli space itself that is described like this. And that is all that I wanted to say.